So it's great to have Madhur here for our Research TTIC talk. You all know, but Madhur is well known for his work in coding theory, complexity theory, graph algorithms, expander graphs, high-dimensional expanders, Boolean function analysis. Today he's going to tell us about List-Decodable LDPC codes. So, you're right.
Thank you. Thanks everyone for coming. Yeah, as I said, also as the title says, this is a little bit about how I accidentally worked on a little bit of quantum coding theory. And whatever I learned and sort of this is joint work with two excellent student collaborators, Shashank here and Tushant, who's maybe not, and yeah, they both flying off to opposite coasts soon. Okay, so I won't get into very technical stuff because I mean some of the algorithmic techniques involve some semi-definite programming hierarchies, quantum codes, need some care, and so I won't get into a lot of technical details. Otherwise, I'll lose everybody, including myself. So, I'll mention some high-level ideas and maybe tell a little bit of a story about some developments as I understand them in classical and quantum coding theory, some kind of nice ideas that came along the way, most of which were not ours, but yeah, I'll tell something about our ideas towards the end. Okay. Right. So, just recalling what we mean by codes, and specifically I'll talk about error-correcting codes in this talk. Okay. And these are ways to protect against corruption when we send messages. So I'm trying to send you a message which is 011, let's say, and hopefully this picture reminds you of an adversary, so it looks somewhat adversarial, which can corrupt some positions in this message, and error-correcting codes are about how to do this so that even after some corruptions, we can recover the message. So we'll only deal with adversarial corruptions. There are also models where you kind of work with random corruptions, etc. We'll not discuss them in this talk. Okay. And this is all classical coding theory, so there's no quantum yet. I'll tell you when we're talking about quantum codes, but right now I'm just sending you literally a string of bits. Okay. And we can do some sort of redundancy. So for example, if I repeat every bit 3 times, I can protect against at least one error. And we'll need to assume something about what is the power of the adversary, because if it's unbounded, it can just kind of always send you the string 0. You'll have no idea what I wanted it to say. Okay. So this is, of course, just to illustrate that, okay, you can protect against bounded adversaries by adding redundancy. And in a nutshell, error-correcting codes are about how to add the minimum amount of redundancy while kind of managing to do maximum amount of communication, etc. And we'll talk about those. Right. The way we'll think of codes is I'll restrict myself to what are called linear codes, and for now we can just think of them as subspaces. Okay. So a code in general is just a subset of strings which I can send, and maybe there's some redundancy properties or there's some ways to kind of figure out what string I meant to send, even if I made an error. We'll think of them as forming a subspace of a vector space. In this case, let's say f2 to the n, and we'll need to talk about maybe larger alphabets, so we can think of fq to the n as needed. Q is referred to as the alphabet size. N is the block length of the code, which is the number of things I'm sending at a time before we start trying to figure out what I meant. Okay, and we'll restrict ourselves to linear codes throughout the term. Everybody okay so far? Yeah, just feel free to stop me even if Nadi is around, but yeah, just stop me whenever something doesn't make sense. It's, yeah. Please, let's all try to make up for Nadi. So, okay. So this is something which maybe I usually give as an exercise, so maybe everybody has seen it in some class at least. But let's just try to look at an example of a code. Okay. So this is an explicit matrix. I wrote down some matrix. We are going to think of it as over the field F2. So these numbers, zeros and ones, are field elements. Okay. And I'm going to define my subspace, but I'm going to define it as the kernel of this matrix, which is just all the vectors which will have length 7, so that I can multiply this matrix and the vector as a column vector. Okay. And such that h times x is equal to 0. Everybody okay with the definition of the subspace? And I claim that this matrix, or this code, which is the kernel of this matrix, can fix any one-bit error. So it kind of fixes the same problem that we were talking about. I tried to send you something, the adversary corrupted exactly 1 bit. And there, if you saw, if I wanted to send you 3 bits, I was actually sending 9 to kind of, here I can manage with 7. So there is less redundancy in this example. Okay. And so we'll think of error as just kind of flipping 1 bit, or flipping is addition modulo 2. So let's say the first bit was flipped. Okay. So I meant to send you a message X. The first bit got flipped, so h times x was 0, but h times this kind of modified stuff might not be 0. Any idea what it is?
0.
Yeah, it's the first column of this matrix. Right? Whatever that is, it's actually the number 1 in binary. So if I flip the ith position, h times whatever I had is just equal to the position that was flipped written in binary. So this matrix actually tells you which was the position that was flipped. You can fix it. It's very nice. It's called the Hamming code. And in general, I will think of subspaces specified this way. I'll think of them as specified as kernel of something. Okay. So that's just a choice. I mean, I can choose to specify a subspace in terms of a basis, in terms of this kernel. But specifying it this way as a kernel kind of has a nice benefit that it gives me an automatic way of checking if something belongs to the subspace. I just multiply it by by h and see if that is 0 or not. Okay. And so if you're old enough to remember when you downloaded something and there was a checksum failure, this is what was happening. But yeah, maybe most people don't know what that is. Okay. And in particular, we'll be interested in LDPC codes. LDPC codes are nothing but where this matrix is row sparse. Okay. So I just need to do relatively few entry-wise multiplications to be able to check h times x is equal to 0 or not. Okay. And that's just how I'm kind of defining this low density parity check, this kind of multiplying and checking something is 0 or not is called a parity check. Low density just refers to sparsity. That's what LDPC codes are.
Madhur, when you say row sparse, you mean like the number of ones in each row is
bounded by some fixed number, let's say 100. Yeah.
I'm going to play naughty, I guess.
Absolutely.
Ask questions.
Yeah.
So I can think of this as a parity check.
It is, yeah.
And I'm just pointing out, I mean, I had to do that translation in my head.
No, that's exactly what LDPC is. It's low density parity check. So H is what I will call a parity check
One of
matrix.
those bits as being a parity of the other.
I'm sorry?
I can think of there being a parity calculation that's...
Yes, so each row tells you a subset.
That you're doing.
And when you multiply, you calculate the parity of those bits in that subset.
Right.
So every row tells you a different parity, and you check a bunch of parities, and you see if they are all equal to 0. That's exactly it.
So this is why it's a parity check.
Yes, absolutely. Thanks. Other questions, comments?
If you look at the generalization of Hamming codes, then you will not consider it a row sparse.
No, it's not. Yeah. So, thank you. Yeah, if I generalize this to kind of larger block length, Hamming code itself is not, or at least if I write this matrix, it's not, it's not an LDPC code, but there's also a nice point that it brings up that, okay, there can, the same matrix can be, or the same subspace can be kernel of 2 different matrices. And I'll call it an LDPC code as long as there exists some sparse matrix. So it may be that the obvious matrix I first chose to write down is not good one, but maybe there is some other one. So
is it computationally difficult? I give you a matrix and you want to find LDPC representation for the same matrix.
I think so, but I don't remember the complexity, but I think it should be infinite. Yeah. Okay, so the title was List-Decodable Quantum LDPC Codes. So we've done LDPC codes. Let's talk about decoding, and then we'll talk about list decoding, and in the end about quantum. Okay. So what is decoding? As I said, we think of a code as a subspace, or in this picture, maybe even a subset of, let's say, vectors of length n over the field f2. Okay. And So the red dots are supposed to be elements of the code, and the empty space in between is just kind of stuff which is not in the code. And I can ask how far are two elements of the code. If I have some way of measuring distance, and we'll stick with, let's say, Hamming distance, so just how many bits they differ in. And the minimum number of bits in which any two code elements differ is said to be the distance of the code. Okay? It's just a lower bound on the distance of any pair of code elements, or also called code words. And then I claim that I can always kind of, if I meant to send you something, we had agreed on a code so that any two messages, which I would have chosen to send, differ in at least delta number of positions. And if I made less than delta over 2 errors, you can figure out which one I meant. Because you can kind of draw a ball around what you received in the space, and then there'll be only one code word in that ball. This is not necessarily a computationally great procedure. So this picture doesn't tell it, but if you're thinking of size n code words, then the number of code words might be exponential, the size of this ball itself might be exponential, and maybe you don't want to actually go through that entire. So this is always possible combinatorially, at least if I have them, but there is still a non-trivial algorithmic problem, which is how to do this efficiently. Yeah.
When you're talking about errors, you just mean substitution errors, like not like deletions or insertions?
Thank you. So by errors, I just mean some unknown positions are substituted. Yes.
Substitutions.
Yeah. There are notions where there are erasures where you kind of know which positions are garbage, and then you can just focus on the rest. We'll not worry about them. I mean, in some sense, those are easy for linear codes because you can do Gaussian elimination. Sort of just ignore them and just focus on the others and solve for the missing ones. At least if there's some bounded number.
And deletion.
Sorry?
And if you delete, like.
Yeah, again, I'm not talking about that today, so we'll just talk about errors in the sense that, some unknown positions are corrupted or substituted. Okay. More questions? David, did you have one? No? Okay. All right. So, this is still a non-trivial algorithmic problem for general codes. How do you find something? For the Hamming code example, which was a very small example, there was a nice, cute way of decoding it just by looking at the number every column represented. But this in general depends on the structure of the code. It's not something which I can tell you without knowing the code. Okay. List decoding is kind of an attempt to go beyond this delta over 2 kind of limitation. So, list decoding is just, okay, maybe the number of corruptions were even more than delta over 2. Can you find me all the code words that are consistent with these corruptions? Okay. And now there are two problems. One, if there's a lot of corruption, all the code words that are consistent with this might just be an enormous number. So how do you prove that there is some non-trivial amount of corruption beyond delta over 2, where there is at least a small number of code words, because we don't want to be kind of considering possibilities where you output exponential size lists. And then there is an algorithmic problem, okay? Even finding one was hard, so maybe finding more is even harder. So can you find? Okay. This is just the list decoding problem. I'm not telling you anything about how to do it. There is a threshold, which maybe I can talk about in my last talk, but there is some thresholds which are known beyond delta over 2, called the Johnson bound, and I'll refer to it later, where the combinatorial problem is solved. But of course, the algorithmic problem remains, and that's actually what I'll focus on today. Okay, we'll come back. Definition, okay? Fine. Let me give you a brief history of kind of LDPC codes and some things that were known. I mean, again, I'm omitting lots of stuff. There are just a couple of points that I want to emphasize in this talk. But LDPC codes have been around for at least 62 years. And Gallagher kind of considered random LDPC codes. And so just think of a random matrix picking sparse random rows. And kind of showed that they are good for, again, random kind of errors, not adversarial. And then Tanner defined codes which are LDPC, which were based on graph structure. And these are kind of useful for our purposes. You're thinking of codes as coming from graphs. And if you have a graph, you think of code bits as sitting on the edges, and on every vertex there is a parity check, which kind of checks whatever the vertex is seeing is kind of behaving nicely. There's some sort of parity check there. And so if this is a bounded degree graph, this gives us an LDPC code. And this is the kind of constructions we'll think about more about. Okay. Although, yeah, I mean, we'll take some LDPC codes for granted. A breakthrough result of Sipser and Spielman from '96 kind of used the expansion of the graph to derive really good codes with a distance which was growing linearly with the block length. The codes had extremely fast encoding and decoding algorithm. You can do it in linear time in the size of the message. And the rate was good, so the size of the message was not much larger than the set of the message that you were planning to send. So, yeah, these were just all around excellent codes. And there was a simpler construction with even a parallel decoder given by Zemmour. And we didn't know list decoding algorithms for these codes in the setting of errors. And I think last year when I talked about, I kind of gave one of one list decoding algorithm for these kinds of codes using the expansion properties. I'll kind of refer to that result, though that's not what we are going to talk about today. But just to mention roughly some things about the landscape of LDPC codes. Yeah.
So I remember 25 years ago, graphical models people were claiming a big win here with LDPC being the decoding algorithm.
So
how's that related to like the
right,
Sipser
good. So there is a way of decoding these codes using linear programs. And then there are these so-called message passing decoders, which can be thought of as basically solving that linear program by local moves. And so that gives also very fast algorithms for it. I mean, generally solving a linear program is not a great thing to do.
My memory is LoopBP did not have any guarantees.
I'm sorry?
My memory is that the LoopBP methods were done without any guarantees.
I think on some graphs they can be analyzed. I don't know if they were analyzed. So there are some guarantees. Like there are some papers with theorems about on this kind of graph structure it performs well. I don't know all of them, but I think in absence of structure you can't give guarantees. More questions? Okay. All of that, all those, so yeah, there are many algorithms to actually do unique decoding for them. So for these kind of codes, you can do message passing, which at least works very well in practice, even if there are not as many theoretical guarantees, but I think there are some. Then there's a linear programming way to do decoding. Again, the linear programs have been optimized and sped up quite a bit by now. There are also these combinatorial or even parallel decoders, so there's lots of nice stuff known. There was no list decoding from what I could tell, and yeah, at least that's this is the only list decoding algorithm I know, and it's much slower. Okay. All right, so let's talk about quantum codes. Okay. And before okay, so now we have this kind of adversary which has maybe some quantum powers, and what can this adversary do? And that's what is the kind of quantum error we are thinking about. Actually, even before that, let's just talk about what we are sending. So we're sending a quantum state, and quantum states in general think of as kind of possibly superpositions of different state a particle can be in. Let's say it's just kind of one particle. We think of two possible states, so we'll call them 0 or 1. And in general, we'll think of them as orthogonal vectors in some vector space, some Hilbert space, so that we can take inner products. And in general, a quantum state can be in superposition, which means that it can be some linear combination of these two. But we don't know what that combination is. We don't quite know. And then we can't look at it because it's called measurement. Once we look at it, it kind of collapses. So we have to do things for these vectors or sort of things which are consistent with linear combinations. Without sort of saying whether if it's a 0, do this, if it's a 1, do this. Yeah.
I'll continue to play naughty, I guess. So the idea here is we're transmitting a quantum state, and it's part of a quantum computation.
I'm sorry?
We're doing some quantum computation.
Yes,
part of that quantum computation involves this transmission.
Yes.
We don't want to disturb, we don't want to measure.
Absolutely. So we don't want to kind of disturb whatever the superposition is because then it will collapse and then I'll not be able to keep working with it. And as David said, you want to think of, these quantum error correcting codes are kind of an important primitive in fault tolerant computation. So you are worried about all kinds of noise that will affect any quantum circuit that you are trying to work with. And so on every wire there can be errors and you don't want to kind of measuring is kind of just destroying that wire, and you don't want to do that. I'll not talk of fault-tolerant computation today. I'll just sort of stick with quantum errors, and I'll only talk very little bit about these as well. But Yeah, so we don't want to, we want to work on it through linear operators, but we don't really want to kind of, in some sense, have an argument which says read it and then do this, because reading is a problem.
Is E unitary or not?
I'm sorry, E will be unitary. Yeah,
Oh,
thank you. I should have mentioned
good.
that.
Just
So an error I will think of as a linear transformation, okay, which is a unitary transformation, so it will kind of maybe rotate the vector. And this will act, again, it's sort of it's consistent with linear combinations. And we want to figure out what to do with it. I'll say very little about this except that, okay, it suffices to kind of consider two kinds of linear transformations which can be generators for all kinds of unitary operations. And this, I'm just saying about one bit, right, or one single qubit, right? I mean, there are many more possibly that we are trying to send, but let's focus on one at a time. Okay. In this, I can look at what are called poly matrices, and I'll just sort of think of the following two transformations, which rotate by 90 degrees, or sort of, maybe flip around the 45-degree line, so 0 goes to 1, 1 goes to 0. And the others which kind of look at this linear combination with equal amplitudes, 0 and 1, and then kind of change the sign. So these are called phase flips. I mean, if you think about it a little bit, a phase flip is also a bit flip. You just rotate 45 degrees and then do this bit flip, right? So just change a little bit the basis, rotate things by 45 degrees, and then you just again do the swap around the 90 degrees. Okay? And a fancier way of saying that is a phase flip becomes a bit flip after a Fourier transform. Okay? So this rotating is nothing but a Fourier transform. So, and again, I'll not sort of talk a lot about why it's sufficient to consider these two, but they can form a basis for the space, or like you can write other unitary transformations as products of these. So we will not worry about.
Wait. You cannot do it. It's on the Pauli group.
I'm sorry. Sorry. Yeah. So not. Yeah. We'll consider about poly errors. Sorry. Yeah. The errors we will consider will be generated by this. Okay. So let's say we can stick with these two kinds of errors. And now, as I said, you have bit flips and phase flips. And in some sense, kind of, again, abstracting away or kind of removing almost all the details, you can think about quantum codes as coming from two linear codes, two classical linear codes. One is supposed to correct bit flip errors, the other is supposed to correct these phase flip errors. Okay. And again, you can work with linear combinations, etc. But I'll just kind of think about this classical problem of correcting these two types of errors. Okay. With this one other property, which is not obvious where it comes from, but we will say if we have Cx and Cz as these two classical codes, then this space which we call Cz perp, which is just a space of all vectors x which have parity 0 with every z in Cz. So all of Cz can form a parity check matrix for the Cz perp. This lies inside Cx. So, I mean, roughly where it comes from is, as I said, after a Fourier transform, a phase flip error is essentially a bit flip error. And if you sort of calculate Fourier transform, let's say, of a subspace, the Fourier transform of a subspace C is supported, of the uniform distribution on a subspace C is supported on C perp. So, a quantum message is basically some code word which is uniform on some subspace. When you do a Fourier transform, Cz perp goes and lies inside Cx, and then you can use Cx, which is just a code in the classical sense to correct bit flip errors, but because we did a Fourier transform, that's also good enough to correct phase flip errors. Okay. So that's roughly where this kind of condition comes from. But if you don't want to think about Fourier transforms, etc., you can just think of it as a problem of designing these two codes, two subspaces. And I should say, this is not all of quantum error correction. This is a special class of codes called Calderbank, Shor, and Stein codes, defined in these two works. And all the recent constructions that I'll talk about, and then most of the known constructions fall into this scheme, but this is not without loss of generality. It's not that any quantum code can be thought of this way, but this is a very convenient way of thinking about quantum codes, particularly if, like me, you are ignorant of quantum error correction and know how to think about classical algebra.
Madhur,
Yeah.
so can you explain, I mean, I don't, like, there are a couple of things that are to me. I mean,
Yeah,
first thing
I
is
should
like,
explain the bottom line.
oh, okay.
Is that what you're asking?
Like, that's what I was about to ask.
Okay,
You asked
no, I
about
should.
something
I-
else before the,
Yeah.
in the red thing that you have written, the definition.
Yeah.
Is there a typo or I don't understand, like Z is in CZ or C is it perp or what is it?
Good. Let's see. You're right. It should be CZ. That's my
Okay,
bad.
okay. That's the definition for CZ perp.
You are absolutely right. Sorry. Okay. And this dot is the dot product of two vectors over F2. It's not an inner product. We write CZ perp and so on, but it's finite fields. It's not really an inner product, etc. Okay. And yeah, I do need to explain what is at the bottom. So I said a quantum code is two classical codes. Okay. And what are the parameters of this quantum code? Because now there are two sets of parameters to choose from. And really speaking, the quantum code is actually this space Cx modulo Cz perp, or sort of the coset space of that, etc. And so the dimension of the quantum code should be thought of as how much is left in Cx once you kind of remove Cz perp, or the difference in the dimensions. And the distance is the minimum of the distances of the two codes, because again, we think of one of these codes as correcting bit flip errors, the other as connecting phase flip errors. And the distance should be related to how many errors of both types we can correct. So the lower, like the code which can correct smaller number of errors will be a bottleneck. So we want both of them to be somewhat good. Yeah.
So a question about, so this CX and CZ are just like certain specific classical codes?
Sorry?
They're classical codes.
They're classical codes. They're just subspaces of F2 to the n.
And when you say, so CZ, like saying phase flip, like you're saying it'll be used to do phase flips in the,
Yes.
but it's not actually like.
No.
Okay.
So actually, yeah, in classical, all I know how to correct is bit flip errors. Okay. So in the quantum circuit, I will do a Fourier transform and then I will apply whatever algorithm I have to correct bit flip errors in CZ after. But if this property is maintained, then I can just do it. Okay. And so from now on, I just need to think of classical codes where I have distance, where I can correct bit flip errors with this extra property. As long as I have that, and so that's basically my only slide about quantum. And now I'm going back to classical code. That's like all the quantum coding I was going to mention. Okay. Any more questions? Okay. The other thing which is on this slide, which is we do want these codes to be LDPC, and again, I don't know anything about the implementation of anything, but in quantum, from what I understand, LDPC structure is a bit more important because we do want to kind of actually physically check whether something is a valid code word or not, or whether there is an error, and there is a cost to implementing larger parity checks. You don't want, and so there's been a lot of recent work on LDPC codes in particular for quantum. And I mean, there are other kinds of quantum codes which can be studied, but we'll only talk about LDPC. We'll not always restrict ourselves to F2. We can think of FQ. Things like subspaces are subspaces. We'll think of fields, and everything kind of carries over. Yeah.
Is your condition the same as saying that Cx and Cz generate the whole space, or am I missing something?
No, it's not. Because it's not a real perp. It's not a real dot in our product.
Because it's over F2.
Yes, it's over F2. In fact, there can be self-dual codes. Earlier conditions were actually that C perp was contained in C.
Good.
And so you don't cover the whole space. More questions? Yeah, this perp notation I don't like, but it's there. It's somehow, it's not the Hilbert space perpendicular or the orthogonal.
No, it's
just a dual space.
still vector space.
Okay. More, yeah.
Are there analogs of GB bound or some 3D constructions?
There are sort of greedy constructions. I think there is a GV bound also. There's like in Gottesman's thesis, I think from '96, he has a lot of quantum bounds, and there are also various books which present the quantum Hamming bound, quantum GV bound, etc. First of all, I don't know all of them, but there are, and then we can discuss them. And they are different. They're not always the same as the classical bounds.
This Calderbank-Shor paper itself is the GB bound.
Sorry.
The first paper, Calderbank-Shor itself is the quantum version of GB bound.
Sorry,
That's how they define this.
I see.
This is what you would get if you wanted to generalize the GB.
I see. Okay. Thank you. Alright, so now we have to find two codes instead of one code. One extra condition, not much more. We know how to find codes. We know how to find two linear codes. How hard can this one condition be? Well, it's hard. Again, this is an abbreviated history. I'm skipping a lot of stuff. But this definition of the CSS code schema goes back to 96. And there were code constructions in 2002, 2003, and I'm not entirely sure about the order of these two. I think these are the published date, but the paper of Friedman, Mayer, and Luo was like some defense report and so on, which was actually released in 2001. The paper of Kitaev maybe was published in some conference before 2003, or like was presented at some conference. This is the journal version. So I don't know the exact order of these, but there are codes known which can achieve distance about square root n, okay, where n is the block length, or n is the kind of ambient space for each of these codes. Square root n is where things stood for a long time, and it's kind of nice to actually see an explanation for it in this Tillich and Zamor paper. There's a nice way to see where the square root n comes from. I mean, it also is that you basically take a product of two classical codes to get these kind of two codes with these kind of properties. And by product, I roughly mean some sort of a tensor product. So you take two classical codes, each of which has distance, some constant times n, there are block length n. When you take a product, you get codes which have block length n square, but the distance remains n. So it's square root of the previous one. Yeah.
Well, speaking for collective Nati,
Please.
Is it general situation, or you still assume some sort of LDPC condition, or it's for arbitrary linear spaces? I mean,
oh, sorry, no, this is LDPC.
LDPC means constant, right?
Sorry, LDPC means constant. Yeah.
LDPC means constant.
Yes. I'm not telling you what constant, and it's not the same constant in all of them, but it's some constant independent of the block size.
Yeah.
Okay. Yeah, it's only LDPC. Thank you. Yeah.
Is there also a dimension?
So I'm hiding that. I'll tell you about dimension later, but I'm suppressing that not to talk of too many parameters.
I should just think of it like a constant fraction of n.
Sorry?
I should think of Cx minus.
Not always. In fact, some of the earlier results had either just non-empty or like constant dimension, then maybe root n dimension. So there are, not all of them are constant dimension or a constant fraction of the block length, but I'm not telling you the dimension. More questions? Okay. And this product view of kind of two codes was useful. It was generalized to things coming from high dimensional expanders in kind of recent works around 2020. And then this sort of issue that n becomes n square was kind of, people tried to combat it in many ways. In some sense, you can write this n square size graph and then try to quotient it by some kind of symmetry so that n square goes down a little bit, and the block length or the distance n is a good fraction of the larger. And you can view many constructions even in between in this way. I'm not writing all of them, but Hastings, Harp, O'Donnell were the first one to kind of go beyond root n in the sense that it was a different power of n. I mean, there were already polylog improvements which came from these high dimensional expanders. And then there were other works. It kind of culminated in these constructions using what are called square Cayley complexes, where you essentially can quotient by lots of symmetries and you really get size n. And these are so-called good quantum LDPC codes, which means that they have distance, which is omega of n, they have dimension, which is a constant fraction of the block length. Okay. Again, I'm not telling you the constants, but now they are both omega of n. And this was a result of Pantalev and Kalachev. And there have also been a lot of improvements and follow-up works and kind of modifications of these, which give codes with efficient unique decoding algorithms, for example, or sort of other nice properties. So this is just some brief summary of some of the results. I'm omitting many, and I'm not telling you all the parameters about the others. Just some data. Okay, so now that we have finally good codes with sort of constant rate, constant distance, we can ask, okay, how good can it get? Like, can we get to optimal parameters? Are there some bounds we can match, and so on? And when you think of larger alphabet size, there is one bound called the singleton bound, which tells you how the rate of a code, or basically the dimension of the code, and the distance are related. And it says that the distance is less than equal to 1 minus the dimension, it's normalized appropriately. That's the classical singleton bound. The quantum one actually has a factor of 2 gap, so it's 1/2 of this, the distance. It's half of the classical one. And in the classical world, there is actually a very nice, beautiful procedure of Allen, Edmonds, and Luby, which can start with kind of codes with some weak guarantees and start with some sort of constant size object which is optimal and give you a really large infinite family of codes which are optimal. Okay? And they match the singleton bound, and I'll say much more about this construction. Okay? And there's a really nice paper of Bergamashi, Golovich, and Gun from Berkeley a couple of years ago, which actually showed that basically AEL can also be done. I'm going to call this Allen, Edmonds, and Luby AEL construction. AEL can also be done for quantum codes, so you can do the same. And I mean, the original motivation was different, the approximate quantum error correction and so on, but let me say what they get in terms of distance amplification or optimal parameters. So using this, start with the quantum LDPC code constructions on the previous slide. They could get quantum LDPC codes with kind of optimal distance parameters. But again, because of the way AEL was analyzed, they could not get list decoding for these codes. Although the distance was really nice, it matched quantum singleton bound. They could also get list decodable codes. In fact, that's what they wanted to get for their application. But then they had to start with something other than LDPC codes for AEL, and they started with some quantum analogs of Reed-Solomon codes or folded Reed-Solomon, and did not get LDPC properties. So sort of you could get either one with really good parameters, but not both at the same time. And the result we get is that, okay, you can get both the properties. And I'll mention a more precise version now. Any questions? This is still vague. I'll mention more precise versions. Okay, so here is a more formal version. Still, I mean, maybe I'm hiding some things. Okay. But for every epsilon and for every rate parameter r that you are interested in, think of both of them as between 0 and 1. There is a family of quantum LDPC codes where the distance is very close to the quantum singleton bound, which is half of the classical singleton bound actually. With an alphabet which depends on how close you want to get on this to this singleton bound, and this is something inherent in AEL kind of applications. And it's list decodable up to Johnson bound of whatever the distance is. The Johnson bound, as was kind of alluding to earlier, is some error radius where we know the combinatorial problem is solved. And this is what we know, for example, for Reed-Solomon code, that we get decoded up to Johnson bound and so on. So saying something is list decodable beyond the Johnson bound requires solving both combinatorial and algorithmic problems. Up to Johnson bound, it's only an algorithmic problem. That one is the one we can solve. But importantly, it's something non-trivial. It's something unique decoding cannot do. So you can go beyond the, and I won't exactly write down the function of the Johnson bound, but last year I kind of talked about new list decoding algorithms using sum of squares proofs, and in particular, the result I did not talk about there was a new algorithm for this anything obtained via AEL kind of constructions up to the Johnson bound. And this is kind of a quantum analog of those results, or an application of those kind of techniques to quantum.
Madhur, if I insist on Q equals also, will your result give anything?
No, it will be useless.
Yeah,
it's large alphabet. For small alphabet, it doesn't give anything useful right now. Yeah, I mean, there are some things we're thinking about, but there is no result here.
Maybe just to help my understanding. So large alphabet is easier because the adversary is sort of limited in terms of how many letters it can corrupt, not like the total amount of corruption. Like, you're not allowed to corrupt every letter.
Yeah. So you can think of large alphabet as saying that, okay, the alphabet size is like 32. It just means that I kind of partition my string into blocks of size 5. Each block is like 5 bits. It has 32 possibilities. But the adversary says, okay, I either corrupts any of these 5 bits and I just count it as corruption. Right? And so when I'm saying that the adversary can do at most 3 corruptions, it can do 3 blocks. It can't really. Otherwise, I would have had to deal with 15 corruptions, which are kind of spread out anywhere. And that's much harder. So small alphabet case is harder. But there's also kind of small, large, and very large. So in some sense, they're like these algebraic code constructions, Reed-Solomon, folded Reed-Solomon, which is where list decoding was kind of most well known, and so most of the techniques lie. And there, the size of the alphabet actually grows with the block length. So for Reed-Solomon, this is the simplest one, you know, like polynomials of some degree, and each position is just an evaluation on a field element. But the field has to have enough elements, so the alphabet size is actually larger, at least as large as the block length. Here, it's some constant, it's some very large constant, but it's independent of the block length. And as Sasha said, the most interesting case perhaps is the one where we can do something non-trivial over a fixed constant size, not an alphabet size depending on the problem parameters, and I don't know that yet. More questions? Okay. So I'll just not say a lot in terms of quantum and classical subtleties, but I'll take this opportunity to just maybe tell you about the AEL procedure, which is really cool. Yeah.
Just to clarify, your alphabet requirement sort of shoots up with this.
Excellent. Yeah.
But the list decoding, like somehow there were a way to make that queue small. The list decoding part would still be okay.
I mean, it depends on how you are going to make that list small, right? Because so somehow the algorithm is saying that whatever is the proof of distance for your code should be expressible in the sum of squares proof system. Then we can solve it well. So if you do this new thing to kind of change the alphabet, is that new thing going to destroy my sum of squares proof or not? I don't know. So it depends a little bit on that. In some sense, AEL is already an alphabet reduction. And it's very nice that it actually happens using an expander graph. You use spectral arguments and I can capture it. That's actually our whole algorithm. So let me just tell you about what AEL does, or let me tell you about what expanders are. Many of you already know, but let's say I'll think of a bipartite biregular graph, equal vertices, n vertices on each side, degree d, and I'll just say it's a lambda expander if the second largest singular value of the matrix is at most lambda. Okay? I mean, I won't use this very precise definition. I'll just think of bipartite expanders, but I'm just saying I want to define them in a spectral way. And we'll just look at this matrix, which is normalized, so the eigenvalues are between -1 and 1. Actually, I'm looking at singular values, so they're between 0 and 1. Okay. And let me just tell you the AEL procedure. If you have not seen it or if you have forgotten it, it's really cool. It's a very general scheme, applies in a lot of spaces, even in quantum. And yeah, let me just tell you what it does. The basic idea is that you kind of take your corruptions that happen, or let's say you have the fact that two code words are kind of somewhat far from each other. You want to say that in a new code, they are really, really far from each other. So, and let's say one of them is zeros, which we can always do for linear code. So you just want to say the number of ones in the other code word is somewhat large. You kind of take those non-zero elements, you move them along the edges of the expander and kind of scramble them around. So if you threw them in random places, there would be differences which would be spread out in a lot of places. And that's what AEL does, but in a pseudo-random way using an expander. So let me explain in a little more detail. So let's say we have a code word which is x1 to xn. It has n positions. It has, let's say, an alphabet size which is already not 2, but let's say 2 to the k. Okay, so that's we think of as q. So each xi is actually a k-bit string or a size k vector. Okay, we take this vector and we then use some sort of constant size code, which we call Cin, or it's called the inner code, which maps k positions to d positions. Okay, so it takes this k-bit vector, moves it to d. Okay, and then we have the advantage that because this is a constant size code, even if the xi has one non-zero bit, C of xi will have lots of non-zero bits. So we'll get lots of stuff to move around. So this inner code is something which is a constant size object. We think of k and d as constants, and this is something which we, let's say, find by explicit brute force search. So now, at each vertex, I have d to the d bits.
So what properties do you want for this resulting code right now? Like the...
let's say I want good distance. And to tell you the punchline, I'll be able to basically inherit the distance of this inner code Cin for the entire big code on n positions. So I'll get distance in a fractional sense. I mean, the block length will be different. Okay, so now for every vertex, I have d bits, which came by applying this kind of inner code. and I have D edges going out of it. So there is one thing to do. You write down 1 bit on each of the edges, let's say. Okay, for now, let's say arbitrarily. So you kind of have some canonical numbering on the edges. You have D bits at each vertex. You write it down on one of the edges. And then on the right hand side, you look at the D incoming edges. On each one, there is a bit written there. You kind of take it. And now you have D bits on the right hand side at every vertex. This forms an element of F2 to the D. We'll think of this as our new alphabet. This bit string that you got at a right vertex is one position on the right. Okay? That's it. So that's all we did. We started from some code where every position had k bits, so alphabet size was 2 to the k. We ended up with something where the alphabet size was 2 to the d. Both are somewhat large, and you need to choose these parameters properly. But both can be thought of as constants independent of the block length. And yeah, I mean, k and d can be linearly related. You just want a good small code, so k can be a fraction of d, or d can be a constant size multiple of k. Okay, that's the construction. It's not obvious that if I start with a subspace, I get a subspace, but if you think about it for a minute, you can convince yourself. Because I'm just kind of moving things around, and when I add stuff, just the sum moves around. The new code, this requires proof, can inherit the kind of parameters, in particular the distance of C0, or distance of C in, which is this constant size object that you put in, and so it can give you very good codes. The previous analyses kind of said that, okay, if you want to list decode the resulting code, you need to start with a base code, not C in, but C0, which is written on the left, this big code on n bits, which has something stronger than list decoding, called list recovery. And so this transformation maintains LDPC property, and again, because we only move a constant number of bits to a constant number of positions. But if you want to use this to design list decodable LDPC codes, well, you have to start with some LDPC code which has something even stronger than list decoding. So it's a chicken and egg issue. And the reason we were able to use the techniques from this previous work is that using sum of squares, you can actually reduce the list decoding of the right-hand side code to the unique decoding of the left-hand side code. That we have for the LDPC code. So then you can make the whole thing work. Okay. Again, lots of details that I'm hiding. And just one thing, I've been lying this whole time. So, I mean, the way this works is if you can capture the distance proof of your code using some sort of proof system, which is a dual of some semi-definite hierarchy, both are called SOS hierarchy and SOS proof system, then you can basically fit it in our algorithmic framework. But for quantum codes, actually even the definition of distance is not captured by sum of squares. Forget the proof of distance of the code, but just it can't really say if two things are at distance 0 or non-zero. And that is an important problem, and this is why it occurs. So as I was maybe saying earlier, if you have these two codes, CZ_perp is a subspace of CX, and it partitions CX into cosets. And the quantum code is really these cosets. So each message is one of these color classes. And two things are the same if they are in the same coset. They can have large Hamming distance. They just have to be in the same coset. So really the notion of distance is given to elements x and y. Is there some coset element I can add to y so that x and y come close? And what is the minimum distance between x and y I can achieve this way by shifting it by an arbitrary element of this CZ_perp. And this itself is a linear dimensional, possibly linear dimensional space. So I'm looking at, I mean, even the definition of distance is kind of an optimization over this F2 shifts. And this is the kind of stuff that SOS is really bad at. So in fact, it was used to show that quantum codes present a lower bound for sum of squares because of this property that can't tell zero and non-zero distances. So and we have a way of kind of getting around this specifically for AEL construction. It's not yet something which I can do for all quantum codes, and probably cannot do for all quantum codes. Okay. But I'll not just get into this detail, but just wanted to mention that there are a lot of subtleties in quantum codes which come from this different notion of distance, or the fact that the quantum code is really a collection of cosets. So one needs to kind of be careful about this when you're trying to apply the algorithm. So that was my big lie, but hopefully it'll come clean a little bit. Okay, let me just mention some future sort of possible questions. One, these algorithms, if you know anything about sum of squares, you know these algorithms are very slow. And past, in some cases, we've been able to get spectral algorithms which are much faster. In fact, it's not inconceivable that we can even get a near linear time algorithm for these AEL kind of applications, although I don't know one yet. As Sasha mentioned, I mean, the case of smaller alphabets is truly interesting. So right now, our alphabet size is constant, but a large constant depending on how close you want to get. And in particular, it's never a pleasant constant. So in some sense, I want like 2. So, and yeah, I mean, there are some things you can say about these alphabet size 2 codes. I'll try to formulate some things about list decoding, but I don't completely know how to analyze it yet. Then I said we kind of go up to this Johnson bound, and beyond Johnson bound, the combinatorial problem needs to be sort of solved. We need to say something about the structure of the code to understand whether we can list decode or not. So let's say something about the structure of the code. Can we go beyond the Johnson bound? Can we actually go up to what's called the list decoding capacity? Even for classical, we don't know this. So yeah, it's and also, I mean, this is kind of maybe a question to the audience, but I don't know a lot about quantum error correction. But in classical world, there are lots of nice connections between complexity and list decoding, and I don't know a lot of quantum analogs of these kinds of connections. So I mean, yeah. So if you have any pointers or suggestions about quantum list decoding, I'll be happy to hear them.